All right, everyone, lots coming at you today. So we've been finding derivatives using the cool new limit as h approaches 0, and we have a lot of algebra, and that gets tough. So I'm about to show you something that will make this a lot nicer and cleaner and easier, and we're going to be fleshing this out over the next few classes. So before I tell you what the power rule is, let's take an example problem and find the derivative of it. So if I have this function, and you're going to have to bear with me for a little bit. It is x cubed minus 2x squared plus 6x minus 3. All right, and I ask you to find the derivative of this. That looks awful, and you would not want to do this. I make you do it one time on the performance task. That is the only time I will ask you to find the derivative using the long method. But I'm going to do it one time, and then I'm going to show you if you can see the pattern developing. Okay? So this is a little bit much. I get it. You can kind of put me on 2 times speed and go through this. I'll do it quickly for you. I feel like I need to show you at least once. There are times where I feel like I have to show you this process just for, if anything, to make you appreciate the fact that there are really cool shortcuts that we're going to start to see. Okay, so plug in x plus h's. Everywhere you see an x. That's the x plus h part, f of x plus h, minus the original function. I'm good. Okay. All over h. All right. So now we get to expand all of this out, this part first. You're going to have to do that. I'll save a little bit of time here because I don't think you want to watch me do a bunch of multiplication. The term you actually end up getting is x cubed plus 3x squared h plus 3xh squared plus h cubed. The next one, we have a minus 2 times x plus h squared. Well, that ends up getting us minus 2x squared minus 4xh minus 2h squared. Then we have this component plus 6x plus 6h, and then that minus 3. Don't forget the back part. Minus, and then distribute all of that. Minus x cubed plus 2x squared minus 6x plus 3 all over h. I don't know what you're thinking at this point. You're like, come on, Mr. West, this is ridiculous. And I agree. I don't expect you to do this all the time. I'm about to show you something pretty fantastic. But I actually kind of like this part. What cancels out? Let's get the purple marker. X cubed should cancel with an x cubed. 2x squared should cancel with a negative 2x squared. Minus 6x should cancel with a 6x. 3 should cancel with a 3. What's left? Well, hopefully everything left has an h term, and I think it does. We have a 3x squared h plus a 3xh squared plus an h cubed. We have a minus 4xh minus 2h squared. We have a plus 6h. I think that's it. Hopefully I did not miss anything. All over h. And now we can cancel the h with 1h from every top term. So this h will get rid of that h is gone. That's to the first. That's to the second. That h is gone. That h is to the first. That h is gone. And then we can plug in this for any remaining h's. So this term right here still has an h in it, so that means it's 0. This term still has an h in it, so when we plug it in, it's 0. And this term still has an h in it, so when we plug h in, it's 0. And finally, we end up with our derivative, 3x squared minus 4x plus 6. That's the derivative. All right. Now, let me show you something very nice. If we had more time and we were together in class, I may ask everyone if they noticed something about the original. Dogs are barking, of course. And the derivative. Ready? This is the power rule. Okay, this is it. Watch how fast. Take the 3, multiply it in front. 3 times the front number is 3. Subtract 1 from the power, you get squared. Did you catch it? Let's do the next one. Take the 2, multiply it in front. 2 times -2 is -4. Decrease the power by 1. 4x to the first. Same thing, ready? Let's do it one more time. X to the first power, take the 1, multiply it in front. 1 times 6 is 6. Decrease the power by 1, which means it just goes to a constant term. And basically the derivative of any constants is just 0. And you have it. That's the power rule. It is a much faster way for finding derivatives of polynomial functions. So power rule is really useful for when you have a number times x to a power. So let me give you the general rule, and then we'll do some basic examples. General rule says this. If you have a function, wow, the dogs are really choosing a terrible time to bark. Oh well. If you have a function that is x to the nth power, the derivative says to take the n and multiply it in front, and then decrease the power by 1. That's the derivative. That's the general rule. So let me show you some examples. All right, examples are, if I have this function, let's do g of x equals -4x to the 8th plus 7x cubed plus 5x minus 3. And I ask you to find the derivative. Imagine finding the derivative the old way, where you literally have to expand out x plus h to the 8th power. That would be awful. You don't have to do that now, though. The power rule says take the 8 and multiply it times the -4. -32 x to the 7th. Take the 3, multiply it in front. 7 times 3, 21x squared. Decrease the power by 1. 5, the 1 in front. 5 times 1 is 5. And that's it. Derivative. Done. No work to show. Hooray. And if you're thinking, are you kidding me? That's ridiculous. I do not believe you're right. All right, let me show you another really cool trick that we're going to be using this year because, again, we're online, and I need you to be correct. I want you to be able to check what you're doing. So I am going to graph this function. Let me show you in Desmos so you can follow along. Here's a cool way to check that your derivatives are right. We can use this all year, so pay attention because I am going to give you a really cool tool to check that everything is going the way it's supposed to using good old Desmos. So let's create a function called g of x, or f of x. You can do whatever you want. G of x, let's plug in the original. -4x to the 8th plus 7x to the 3rd plus 5x minus 3. There's the function. I don't really care about the graph. I'm just going to use Desmos for a cool feature it has. Okay, so that was the original. Now my claim was that the derivative, I'm just going to call it y. My claim was that the derivative was -32x to the 7th plus 21x squared plus 5. Okay. So that's my claim that the derivative is this thing in blue. Again, I don't really care about that. Instead, what I'm going to do is something pretty cool. Desmos has a built-in feature. It can graph derivative graphs for you. So you use this notation. Ready? You go d over dx. And you tell it, hello, Desmos, I would really like it if you graphed the derivative of g. And what do you notice? That graph is exactly the same as the derivative we found, which means, yes, we found the right derivative. This thing that I thought was the derivative really is the derivative because I'm getting the exact same. This function I created is the derivative of the g function. We'll get a lot more into derivative graphs later, but this is an awesome tool to start getting used to what derivative graphs can look like. There's all kinds of connections we're going to have to make with this stuff pretty soon. But for now, use Desmos as a way to check that your derivative is right. Okay? So let's move on. Let's say you had a problem like this. Another example. This is a second example. What if I gave you this function, h of x equals 2 root x? Well, this is another one of those ones. Oops, sorry. This is another one of those ones where you'd have to go through and do the whole conjugate thing, right? Because you're like, man, it's not a polynomial. But if you can write it as a polynomial, you can use the power rule. So this is where you got to remember something. Radical x, there's a better way to write this. And if you had me for accelerated, I probably told you that I like the other way of writing these better, and this is why. I can write radicals as fractional exponents. So I can write the problem this way. And now to take the derivative, I multiply 2 times a half. Those cancel, it's just x. And then subtract 1 from the power. That gets me negative 1/2. And then I would take that answer, but that's the same as, again, a negative exponent goes to the denominator. And that's the same as just this. Oops. So what I'm telling you is, if I have this, the derivative of that is that. So for example, let's go back to the old way of thinking about derivatives real quick. Let's say I wanted you to find the derivative at 4. Well, if you plug it in, you'd get 1 over radical 4, which is 1/2. Don't forget, that's what this really is all about. This is the slope at x equals 4. Let's go back to the graph real quick. I'm going to get rid of these. Well, actually, I'll just put it right here. So if we go back to this curve, it's 2 radical x. I asked you to find the slope at 4, which is this. And does it look like 1/2 is a logical answer? Yeah. Rise 1, run 4. Rise 1, run 2. That looks logical. But now using our sweet new strategy, we can actually find out if our derivative is correct. We call this g of x. Let's get rid of this one. We write down what we thought was the answer, so I'm going to get rid of this guy. We say, okay, I think the answer is 1 divided by root x. So this black function right here. And ready? Let's see how we did. Okay, graph the derivative of g. Nice. It's on top of it, but it is highlighting it. Can you see? There we go. That's better. Yeah. So we know our derivative is right. We got the same graph by saying graph the derivative of g as we did by actually graphing what we found the derivative of g to be. And that is an awesome strategy. That's what I want you doing. There's no reason not to have right derivatives if you have time to check your answer, because you'll know right then and there if it's right or wrong. All right, so one more example, and then I'll let you kind of put the pieces together. And we'll practice a bunch of these. That's what we're doing for the next few periods, is kind of practicing these. One more type of problem we've seen. What about a problem like this? Where you have a rational function. This one just has x squared in the bottom. Oops. A problem like this. Well, you're like, dang, that x is in the bottom. Can I do this one? Yes, you can. You just need to rewrite this using, and I kind of gave it away in the last problem, you can use negative powers. Cannot you write it this way? And now to find the derivative, you multiply by the power. Multiply by the power, which is negative 4 times x, and then subtract 1 from the power to the negative third. And then you can rewrite it, which is negative 4 over x cubed. And now let's check our answer and see. So real quick, we could do it the old way where we find the slope at the point, but I just want to check to make sure that this is actually the right derivative. Did this strategy actually work? I'm skipping a lot of the proofs for you guys. Sadly, I love proofs, but let's check to make sure that this actually worked. All right, so we have our function, which was 2 over x squared. And we just thought that the derivative was negative 4 over x to the third. Okay, so again, we don't need the original function to be graphed. All we care about is this is what I think the derivative is, and the moment of truth, is it? It is. Same exact line. It doesn't matter what it looks like. It will matter soon. So it's kind of cool if you're actually looking at these derivative graphs a little bit, because the derivative graph is going to be a big part of where we go in this class. But for now, just use it as a way to check that your answer is correct. There's the derivative graph, and there's the original function. And we'll get a lot more into derivative graphs later. But it actually is pretty cool. So check this out. If I graph them both on top of each other, you're telling me, for example, like right here, the purple one is the function. And you're showing me that the slope there, or the slope should be about, looks like if I go down 1 over 2, so negative 1/2, and look at the value of the derivative graph. It is negative 1/2. So the derivative graph's value is the slope at this point. You should go back and listen to that again, because that's a huge deal. If you can start to wrap your mind around that the derivative graph's value is the slope of the original function, that means you're starting to put these pieces together. That's going to take some time, and that's my job to help you out with that. All right, let's do one last kind of overall crazy example. So if you think you got it, you can move along, but I'm going to do one last putting it all together. So if we have this function, and we have 5x to the 5th minus 3x plus 3 root x minus 1 over 5x, like that. Let's find the derivative. Well, before we do anything, let's rewrite this so that it's a number times x to a power, a number times x to a power, a number times x to a power. This one's the tricky one that everyone messes up every year. That 5's on the bottom, keep it on the bottom. Just bring the x up and change the, dang it, sorry, I'm on the wrong screen. Okay, so again, we have this function. I'm trying to find the derivative, so I'm rewriting it. So right here, I rewrote it as a number times x to a power, a number times x to a power. I changed the radical x to x to the 1/2. And look, this was 1/5 and an x in the denominator. All I did was bring the x up to the numerator. That 5 has to stay. Now we're ready to take the derivative. The derivative is multiply 25x to the 4th minus multiply, and the x goes away in this case, plus multiply 3x, 3/2 x to the negative 1/2, multiply, negative times a negative is positive, x to the negative 2 power. And I don't really care if you keep your answer like that. It shows me that you understand the power rule for now. So I am okay with that. And lastly, let's check it and be done with it. So the original function was 5x to the 5th minus 3x plus 3 radical x, and then minus 1 over 5x. The derivative that we just found was 25x to the 4th minus 3 plus, looks like 3/2 x to the, I'm literally just going to be lazy and keep it as it was, negative 1/2, and then plus 1/5 x to the negative 2. Okay, moment of truth. Let's get rid of the purple function. I really hope that the derivative of g is right. So good. Same function, the derivative of g equals this thing that I calculated the derivative of g to be, which means that everything checked out. And just so I can show you one more time what I was saying in the last problem, this is pretty cool. If we look at the purple function, the original function, it looks like at, let's look at 1. 1's pretty far. Let's look at half. So at the value of x equals 1/2, which is right here, it looks like the slope is about a rise of 1 2, somewhere around 1. I mean, I could believe it's anything close to 1. It's looking like the slope is positive 1. So at 1/2, it looks like the slope is 1. Let's see if that's what the derivative graph is telling us. Where did you go? Yep. It's telling us it was a little bit more than 1. So, I mean, but I was within 0.2. Not too bad. But this is pretty cool. Look what it's saying. It's saying the derivative was a positive value that got shallower and shallower, and then it started getting steeper and steeper. The derivative got less and less, and then it got more and more. That's a lot of calculus right there. So if you're understanding that part I'm saying right now, that's going to be what we're doing for the next month or two, is a lot of this looking at derivative graphs and how do they impact the original function. But for now, I need you to be able to find derivatives using the power rule. All right, so your homework's going to look a lot like this, just practicing the power rule. And we'll learn other tricks soon too. So this doesn't really help us with problems that look like this. So if I gave you a problem that looked like this, lame, you're still out of luck. That's something else, okay? So we still can't do those. We still can't do these yet. We're still out of luck. But we'll get to those soon. So stay tuned and good luck.